second part of this presentation, Synthetic Geometry of Our Life World, in which I will introduce you the topic of synthetic geometry. This topic is more abstract, more like mathematics, but for this reason also simpler. It has less ambiguity. Without further ado, let's see what synthetic geometry is. When we try to explain a phenomenon or decide between different explanations of this phenomenon, we can do this from two different angles. Either we look for a real-life instance of this phenomenon and start to describe it in all details and to measure it. However, this is only possible if there is no controversy about the terminology and measurements used for it. These types of methods are called analytical. It also relies on material observation and is therefore barely applicable to transcendent problems, given that transcendence implies a non-material component that escapes any possible measurement. What is synthetic geometry? Synthetic geometry is such a formal system. Wikipedia defines it with the following words. Synthetic geometry is geometry without the use of coordinates. It relies on the axiomatic method for proving all results from a few basic properties, initially called postulate and at present called axioms. This method was introduced by René Descartes. In 1957, Émile Martin, in his work Geometric Algebra, proved analytical and synthetic geometry to be equivalents. Since then, synthetic geometry has come into disuse, at least in geometry. My knowledge and understanding of geometry is not sufficient to make any further statements on this. As for philosophy, the formal approach retains its importance. Paradoxically, we call the use of logical axiomatic systems in philosophy analytical philosophy. It became more popular through the linguistic term and relies highly on language. Its importance becomes even more evident when dropping the names of some of its prominent representatives such as Gottlob Frege, Bertrand Russell, Ludwig Wittgenstein, Rudolf Carnap, Wyatt van Orman Quine, Karl Popper, Karl Otto Appel, Saul Kripke, and David Lewis, on which some of the most influential philosophical streams are based, such as the Frankfurt School and the Kyoto School, and which gave life to a unique approach in philosophy, argumentation ethics, with representatives such as Frank van Doon or Hans Hermann Hoppe. If you do not know these names, it is not a problem. This is only to illustrate that axiomatic approaches are very much alive in philosophy and strongly opposed to empirical methods, which apply calculations and measurements to the observation of real-life objects. If you are interested, you may search these names on internet. Even though there are philosophers who believe that anything can be explained with empirical methods, there are good reasons in philosophy to use analytical methods, which means axiomatic methods, such as synthetic geometry. Why should we use synthetic geometry? Well, for example, when we want to study objects that have known or no sufficient data to which we can apply analytical investigations. This is the case for all transcendent objects. We can only measure the material aspect of them, but not their real or total aspect. Further, it can be helpful when intuition is misleading, which seems to be the case when speaking about time. Evidence for it is that different languages have very different understanding of time. Finally, such formal systems can be used as a frame or a red rope that orients among the manifold theorems, corollaries, porisms, and problems. It can help to relate and order them in a coherent way. This makes inconsistencies and problems more visible and helps also to memorize better. Down here we have a representation of parallel lines and how they behave in different mathematical systems. Parallel lines are not out there in the world, they are patterns of our mind. And this illustration is an axiomatic representation. That means this image tries to make a scheme of the ideas we have about geometrical spaces and how lines would behave in them. It is not something that we necessarily find in our everyday life. Synthetic geometry makes use of primitives, basic notions, and terms, well-defined words or phrases used to explain something formally. Here we have an example of primitives in geometry. The most basic concept in geometry is the point. It models an exact location in space and has no length, width, or thickness. We already see that axiomatic models have nothing to do with our intuition. This point here in the illustration should actually not be visible to our eyes. This is why mathematicians used to make a cross and not a dot when representing a point. Connecting two points makes a line, connecting lines makes a polygon, and connecting polygon forms a solid. The formation of all these shapes in the former slide is based on axioms. For each step we use a rule, an axiom, which is a statement about these terms. For example, given 2 points, P1 and P2, we can fold a line, L1, connecting them. This means we have two primitives, the points, and one statement. The connection between 2 points is called a line. This is a statement. In many aspects, this is nothing else than a definition. We cannot really argue about a statement. In order to make an argument, we need something that helps us to decide if a statement is true or not. This means we combine axioms through logical expressions. Logical expressions are, for example, to say that two things are the same or different, or that one thing causes another, or that something belongs to the same category than another, etc. Thus, an argument is the logical connection of premises or assumptions into a truth statement. When we start building on such truth statements, so-called arguments, and when we do this in a coherent and consistent way, we call it a theorem. One of these theorems, of which most people have heard, is the theorem of Pythagoras. Within this simple illustration and a basic calculation, a squared plus b squared gives c squared, we contain a whole theory about how to measure any right angle anywhere, for example when planting trees in parallel rows out in the field. Combining such theorems into a whole set of coherent and consistent connections We only need to add a formal proof, something that tells us if the theorems or their combination is true or not. This gives us, finally, an axiomatic system. In a certain way, we can say that an axiomatic system is a formal language, such as computer language. But we can also model our natural language into an axiomatic system, as long as we do not expect it to be completely complete and coherent at once. Let's have another look at the block universe. The principal scientists who contribute to it are Hendrik Lorentz, Henri Poincaré, Albert Einstein, and Hermann Minkowski. They defined the block universe with the following parameters. There are two types of dimensions, space and time. Our world is made up of 4 dimensions, which are composed by the 3 dimensions of space and the 1 dimension of time, together called space-time. Even though there are mathematical theories that could defeat this theory, which means that could prove it wrong, this is not bothering us here. What is important here is that we have no useful application to social sciences, but the social sphere also forms part of our world. Intuitionist mathematicians offer a better approach, but this approach was not known to me when I developed my theory. I shall certainly test the implications of it in the future. For the moment here, this is not of our concern. Between 2009 and 2015, when I worked on my theory, I simply stumbled over a large number of problems that space-time created in a social world. First of all, space-time had no concluding solution for the problem of identity. Therefore, I needed to rethink the whole concept of time and space from the beginning, and I invite you to do this together with me now. For those of you who like science, I offer here a link to Nicolas Geezing's presentation Time in Physics and Intuitionistic Mathematics in Numerosity of 2021. It is surprising how he names many of the difficulties found in the block universe that also created problems to my work. If you are not a fan of mathematics, however, I propose you just jump to the next slide. In the field of physics, another scientist worked also with the problem of time and inspired me very much. This was Etienne Klein from the CA Pari Saklow. In his article Le temps existe-t-il? Does time exist? He proposed that a good way to understand better complex problems, we can sometimes try to imagine them without words. This is what he did with time, and watching his presentation, I intuitively discovered that there was an option he had not considered, because he had limited his drawings to a two-dimensional projection. To add a third dimension opened up a whole new understanding of time. Consecutively, I applied the central concept of time to the question what it means to be a person, how it connects to interpersonal communication and language. This is a little exercise I did around 2011. With this, I shall conclude my explications about what it means to work with synthetic geometry, and in the next part I shall guide you through a description of the whole axiomatic system that I had developed.